Arthur is going to put a walkie-talkie close to a board with two amplifiers. Notice how much noise it will generate, and notice one amplifier will be better than the other. Why? You will see. Let's start.
I'm going to just right now apply the walkie-talkie noise to the circuit, and what you can see is that amplifier number 2 in yellow is much more sensitive to RF. And later we'll look at the theory behind this, but basically some amplifiers have they have a built-in internal EMIRR, or electromagnetic rejection ratio filter. And so this filter eliminates or minimizes the effect of interference. And so one of these two devices has that filter and the other does not. And so this is set on a 200 millivolts per division scale. And so we're looking at fairly large perturbances from the walkie-talkie. But we can also look at intrinsic noise. So the walkie-talkie is generating extrinsic noise, but we can also look at intrinsic noise.
So what is difference? Extrinsic, it means it's something what is coming from outside, and it's causing the disturbance. And the intrinsic is what?
The intrinsic is noise generated by the parts itself. Resistors, for example, generate intrinsic noise. The random motion of electrons within the resistor will generate noise. And so the larger the resistor, the more the noise. And actually, the higher the temperature, the noise will also increase. Semiconductor junctions as well will generate intrinsic noise. And so we'll look at a little bit of the theory about that later, but the nice thing about intrinsic noise is it's very easy to predict. Mm-hmm. You can do it with simulation, calculation, and those two methods will give you virtually the same value that you measure. So it's pretty good at predicting, whereas extrinsic noise, and examples of extrinsic noise, we're looking at a walkie-talkie, but certainly any high frequency source, such as a cell phone, but even low frequency sources like 60 hertz noise, or noise generated on the PC board itself, like switching from a power supply or digital communications. All those are forms of extrinsic or man-made noise. And intrinsic is kind of noise generated by the components itself.
Mm-hmm.
So what we're looking.
So if someone is designing like super sensitive analog circuits, they need to be aware and careful about also this intrinsic noise, correct?
Yes. So let me just show you that. So if I put this jumper in here, what we're doing is we're connecting a filter, and you can see when you connect that filter that the noise, the intrinsic noise of the amplifier, dramatically reduces. And sometimes people will ask me, well, just filter everything and get rid of that intrinsic noise, but your signal of interest is also being filtered. So you can only filter to the degree that your design allows. So some designs require high frequency signals, but if your design requires just low frequency signals, you can limit the bandwidth to that low frequency and minimize the noise in that way. So I can remove the jumpers, and you can see it's quite a substantial increase in noise.
Mm-hmm. Are there like different filters? Because the yellow line is like even a little bit better than the red one.
Yes, the two filters in this case are the same, but it has a larger impact on the yellow signal because the noise is basically greater for that one. You know, the bandwidth of the two circuits is being limited by the same RC filter. In fact, I could pull up the schematic of it and show a simulation.
Okay.
So this circuit right here is the actual schematic. It's two amplifiers, mm-hmm. And I have the OPA 211 and the OPA
So each
188.
channel has 2 amplifiers, correct?
Yes,
Okay.
yes, it's a dual amplifier. And you can see this switch here allows me to connect or disconnect the filter. The component values are the same for the two, but the noisier device, it turns out is actually the one that is usually considered to be the lower noise of the two. The reason why this is noisier is because there's a higher current noise. So you can have voltage noise and current noise, and that current noise flows through these resistors and is amplified by both of the stages.
And the filter is
So
basically the C6 capacitor?
that is correct, yes. So if I run the simulation on this, oops, simulation. So I just say noise analysis, and this is Tina Spice. It's a free program that TI provides. There's two different kinds of noise that we'll look at: noise spectral density and integrated noise. So integrated is called total noise, and noise spectral density is the output noise. And we'll see it from 1 hertz all the way up to 100 megahertz. And if I run this simulation, this is the noise density, so it's noise in nanovolts per root hertz or volts per hertz. And then
what does it mean, noise
shows,
density? It's like low frequency is the biggest part of the noise?
That's true.
Okay.
It's the noise per unit frequency. Right here it's shown in a linear axis, but usually it should be shown in a logarithmic axis, and it gives you a little better idea of where the noise is. So this region right here is often called the 1/f region. This is the broadband region. And then this region is where the filter kind of turns on. And even though the noise is higher at low frequencies, usually the higher frequencies will dominate because this is a logarithmic axis and there's a lot more content here at the high frequency. So I did this simulation with the switch closed, and the total noise, and this is what you would measure on the oscilloscope, integration of this noise density. This total noise is about 580 microvolts RMS. And if I do the same simulation, but I open this switch.
So without filter.
Right, no filter. Let's see what happens. So it's easiest if I just copy this curve. So I'll just Control C, and I'll just paste it on top of this noise curve. Oops. There we go. So you can see the dramatic difference. This red one down here is
this is with the filter.
That's with the filter, and then this one is without the filter.
Okay, what do we? Why did you use this integration? What does it mean?
It's quite different, and well, so what we're looking at in the density, the noise density, is the noise per square root hertz. It's really the power per hertz, and that's a strange unit. You know, noise per root hertz or power per hertz. And what we have to do is for the voltage noise density, which is what we're seeing here, is you really square it. So you convert it to volts squared per hertz, and then you integrate it. And when you integrate it, you then get basically volts squared, and then you take the square root of that, and you get volts. So we're basically adding up all the noise power from 0 to essentially infinity, but as at the point where it's rolled off a great amount, it becomes inconsequential. And so integrating it tells us how much total noise there is
for each
or
frequency.
what the, yes, at all the frequencies combined.
Okay, so this
so
is
when
the
you look
important
at,
graph. This is telling us that from 10 kilohertz higher, there is a lot of noise if there is no filter.
yes, and the other graphs are interesting in terms of, if we look at those two on top of each other, you can see that what's happening with the filter. So let me change the color of this to make it a little bit more obvious. So you can see that this is the one without the filter, and this takes the noise spectral density and rolls it off somewhere between 1 hertz and 10 kilohertz. All this extra area under this noise density curve is what generates that extra integrated noise. And so really, if I wanted to reduce the noise of this circuit, there's a couple different approaches. One is I could change the resistor values. I could use the same ratio, so I'd get the same gain on the amplifier. But by reducing the resistor values, I consume a little bit more current, but I generate a lot less noise. The other is I could add a filter. As I mentioned earlier, you could filter to the extent that your circuit will allow. You know, you might have a 100 kilohertz signal that you're trying to amplify. And if you cut the bandwidth of it to 10 kilohertz, then you've basically defeated the purpose of your circuit. So you need to set your bandwidth to whatever your signal requires, but to the minimum bandwidth that is necessary to minimize the noise. I could also put a filter on the output of this amplifier, or even a filter here. So this is just a simple demonstration, and by putting a filter here, we could further reduce the noise, and we could also reduce the resistors here. So each resistor, each amplifier will generate noise.
Okay, and you said the noise is also, it depends also on the size of the resistors, for example, or like component, physical size of the component?
No, the resistance magnitude.
Resistance,
so,
okay.
So for example, I can make the same circuit,
okay,
and I can change this to 10K and change this to 100 ohms.
Okay.
And now the gain of this circuit is set by the ratio of R8 to R12 plus 1. It's a non-inverting amplifier. And so by doing this, I will get a little bit less noise. So if I do the noise analysis again,
this is interesting because I think anyone who would like to simulate their own amplifiers, now they can see how they can do it and what they should choose and how to understand the results of these simulations.
Yes. We use the noise simulation frequently. Okay, here it is. So here's the one with the original resistors, the filter, the unfiltered. Now, I'm right now in the unfiltered position, but I reduced the noise of the resistors. And you can see by reducing the noise of the resistors, we dramatically reduce the total noise. And the only real trade-off here is that we're now wasting more power because current's going to flow through those smaller resistor values.
Okay. And the simulation results are same as what we measure, you mentioned?
Yeah.
Can we compare it? I'm just curious.
Yes. So let's take a look at, well, first let's get the values.
So how we can measure this noise on these, what is this? This is oscilloscope or what is it?
Yeah, this is a virtual bench oscilloscope. And so we're measuring the noise basically. It's 20 millivolts and 10 millivolts per division. And you can see it's showing me the peak-to-peak values over here. And the value that we get in simulation, this is the RMS values. Now, when you think of a sine wave, if you multiply the peak by 0.707, you get the RMS, but it's a little different for noise. Noise is a Gaussian distribution. We'll look a little bit more at that later, but to find the peak-to-peak, given an RMS value with noise, you multiply it by a factor of 6, and it's really 6 standard deviations. So if we look at this curve right here, it's about 10.75 millivolts RMS. And here it is. That's the OPA 211, which is the bottom curve. So 10.75. If I just take that and, well, I don't even need a calculator. Yeah, it's about 60, right?
Yeah.
So let's take a look at that. All right. So here it is. It's 64, 65, and so forth. So it's actually quite accurate. And it'll bop around a little bit, but if you were to take a lot of data and pull it into Excel and calculate the standard deviation, that would be more accurate than what we're getting here, this peak-to-peak value.
And what is different schematic in the red line? It's just different amplifier. It's different component, correct?
So, so let me pull up the simulations. So if I compare one, this is the one that we're looking at there. That's the OPA 188. And if I do the analysis of that one.
So this is the red one?
This is the red one, yes. So if I do that. Okay. Let's compare this one. So here we're getting about 3.5 millivolts, 3.6 millivolts, and RMS. So multiplying that by 6, about 180, something like that. So let's take a look at
20 something. Yeah, 20. Oh yeah, you are right. Okay, this is cool.
So yeah, and you could do the same thing for adding the filter. But you know, one thing about this I should mention, it's an excellent instrument, but and this applies to really any oscilloscope, when you're measuring the peak-to-peak value, it's not really the same as getting the RMS, which is essentially the standard deviation of the signal. And so you'll get a few spikes that will be outside that region, and that's going to give you a little bit of a different answer here. In fact, with intrinsic noise, the more points you collect, the higher the peak-to-peak is going to be, because it's a Gaussian distribution, and the more points you collect, the more likely it is you're going to be on the tails of that distribution. So the best way to analyze this noise values is to look at the standard deviation. And we'll see that in the next demo. Should I pull up the next demo?
I'm just thinking, so I think this is like super good example to show how important this filter can be, because it can really clear up this signal, and that's basically the reason why in amplifiers there is this small capacitor across the resistor, because it's helping a lot.
Yeah.
So if someone needs like very clean amplifier, then they should simulate these kind of filters and use them in their circuit.
Exactly. And even your sensor is going to generate noise. Your A to D converter, basically all the circuits in your board will generate noise. The voltage reference connect the A to D converter, the A to D converter, it all will generate noise.
So let's have a look on the AD converter. You have demo also for this one.
Sure. Okay, so this one.
what do we have for AD converter? What is on,
So
on
this
the
is
board?
the evaluation. Sorry, we've got a visitor at our house.
It's okay, don't worry.
So here's the A to D converter, and what we'll look at is, so let me show you physically the hardware. Here's the hardware. We've got an amplifier connected. Right now I have a DC signal that's built into the board being applied of 0.1 volts. The amplifier is in a gain of 10, so what we should get is about 1.1 volts out. Yeah, and it's in a gain 11. So, if I change this to auto fit, the whole range, the range of this AD converter is 5 volts. And so you can see we're getting about 1.1. And this is what the noise actually looks like.
Well, okay, I would like to understand a little bit more. First, what is this software?
So this is software for an evaluation module, which is what this is. The evaluation module has a digital controller, and it has multiple different options. This particular one is kind of part of our training series called Precision Labs. And we're looking at a SAR data converter, and we're connecting to it an op amp, a 5-volt op amp, and putting 0.1 volts.
I understand that, but so the board is connected through USB, and then you have this software which can read data from the board and from different devices which are on the board, correct?
Yeah, yes. And if you look at the software, you can see we're sampling at 1 megasample per second. So each microsecond we get a sample. We're doing 262,000 samples. So this is really the time domain display. And you can see all the 262,000 samples. And we can also have a frequency display, frequency analysis. But in this particular case, we're not applying any AC signal. So it's just basically showing us the noise floor. And then what's really pertinent to noise is a histogram. So I mentioned that intrinsic noise has a Gaussian histogram, and that's what we're looking at here. But I'm going to put this in continuous capture mode, and it'll just keep collecting those 262,000 samples over and over again. And if I use the walkie-talkie on this, you can see that what we get is a non-Gaussian distribution. And that's because we're essentially interfering with this device. We can look at that in the time domain as well. Oops, I have to stop this.
So basically, if we need to recognize if there is this intrinsic or extrinsic noise, then we can have a look on this distribution, noise distribution, and we can see which one we have.
Yeah, that's that. And you can look in the time domain as well. What happens when you apply an RF signal to a low frequency op amp like this 1 megahertz amplifier is it shifts the offset. And as I mentioned, some devices have better rejection of this RF than others, and that's what the EMIRR, electromagnetic rejection ratio, does. And so you could see in some of the examples that we're shifting the offset.
Okay, now we have this noise. So what can we do to minimize it?
Well, let me do one more thing I'm going to show you is the frequency domain. Because this is pretty interesting.
We should see some peaks, I guess, at the frequency where the walkie-talkie is working. Maybe, I don't know.
Well, yep, you're right. In a sense, you're right. And the reason why I say not exactly is because the frequency is being aliased back. The sampling rate of this data converter is only 1 megahertz, and so you could see that the last time I took a sample, it was at 30,000 or 300,000 hertz. But this is a 250 megahertz, output frequency. So what's happening is it's aliasing back, and it's also causing the amplifier's offset to shift. So, so even though the output frequency of this this walkie-talkie is much wider than the bandwidth of either the amplifier or the AD converter, it still shows up in the frequency domain and in the time domain.
That's interesting. So basically, you can get noise even from the devices which are working on higher frequencies than what you are actually processing, or what are the capabilities of your device.
Yeah. Yes. Now I can show another demo where we can connect longer leads to this, and we can see 60 hertz pickup.
Okay.
Should I do that?
Okay. Yeah.
So I'm just connecting. I'm connecting a battery to this, and the battery has a little voltage divider on it, and the voltage divider is just making the input voltage 0.1 volts. So very similar to what I did when I had the source here, but now it's from an external source. And ideally, you would want to kind of to the next point, but I'll mention it now. You'd want a shielded cable, but I'm kind of intentionally making things bad, so I have these wires all spread out, and I'm going to move this over by my lamp, and so it's going to be really bad situation that you don't want to do. And just to illustrate the 60 hertz pickup.
So basically, we have battery connected to AD converter, but through very long wires.
Yes, and you can see it if you were to. I'm going to turn off the continuous capture.
Wow.
Okay, let me just capture one frame because I want to. There we go. You can actually see the 60 hertz modulating the noise, but I find it even more interesting to look at the spectrum. And now we can zoom in on this area here, zoom in further, and you can see 60 hertz, 120 hertz, and various harmonics of 60 hertz. And so 60 hertz is a major problem here.
Oh, wait.
Sure.
Go back. The first one is 60, but the second one is like 90, no?
60, right. It should be 120. I don't know why it's at 90, to tell you the truth. So we should have harmonics of 60 hertz.
Maybe you move the wires different way.
Yeah. And then if I look at the, let's look at the histogram. So the histogram, it still looks Gaussian, but in fact, it's not completely Gaussian. And what is a little different is the tails of this histogram are much further out. So if you look at the peak-to-peak value here, it's much higher than it would be for the normal 60 hertz noise. And in fact, just depending on the conditions of your room, whether the lights are on, the lights are off, where your wires are sitting, you can make this worse or better. And that's the dangerous thing about the 60 hertz. Sometimes when people do low noise measurements, they'll turn off all the lights nearby and try and minimize the power, or run things off of batteries if they have to, or use shielded environment as well.
Okay, so what can we do with this? How can we remove this noise?
So shielded cables, shielding the board itself, or the test test design, whatever it is, the test board. Of course, you have a lot of videos on the idea of doing good printed circuit board layout, and anything that's on the printed circuit board, your switching power supplies, your high-speed digital communications. If you don't use good PC board practices, you'll not only cause maybe data integrity issues where you get communications errors, but you'll very often will get problems with pickup of that digital signal into your sensitive analog. Keep in mind that the resolutions that we're looking at here are quite small. So we're dealing with millivolts. In this case, often we're dealing with microvolts or even nanovolts that we're trying to measure. So we'll have 24-bit delta sigma converters that measure signals with least significant bits in the nanovolts, and so 60 hertz pickup could be quite problematic there. One way that you could minimize noise in that case is sometimes there's digital filters. So we talked about analog filters, but the A to D converter itself can have a digital filter, and it may have a notch at 60 hertz or 50 hertz, depending on the region. And
so you mathematically remove the 50 hertz from the signal?
Yeah, exactly. You'll just notch it right out. And digital filters are pretty flexible. You can have different kinds of digital filters that will act more closely like an analog filter.
So for AD converter, normally you don't really use a filter on the input. You can do everything digitally.
Well, you do. You still use filters on the input. And to the RF example with the walkie-talkie, there's no digital filter that's going to eliminate that. So you would want to get rid of that filter or get rid of that high frequency pickup with an external filter. If there's an amplifier, the filter could be on the amplifier or before the amplifier. Sometimes
and it would be same what we were talking about or already.
Yeah. Sometimes the A to D converter will have a simple RC filter on the input, and it just connects directly to a sensor. So it can eliminate high frequency pickup, RF signals. And then, as I mentioned, some of our devices are a little bit more robust against noise. So there's a spec in the data sheet that you can look up, EMIRR, or electromagnetic rejection ratio. And if it has good rejection, then if you pick up some noise at very high frequencies, it'll eliminate that or minimize it. And if the EMIRR is not as good, then maybe you might have to look for some other approach to kind of minimize that noise.
Okay. So now maybe we would like to move a little bit into theory and understand a little bit more what is happening there and why we have these kind of noises.
Sure.
You don't have any other demo or simulation, correct? We show everything.
I think we've seen it all. Yeah.
Okay.
So let's take a look at the theory. So what I showed you was simulation of noise, and that's relatively easy to do. But the problem is with simulation that you can actually simulate something, and if it's not connected correctly in the simulation, or if the model isn't correct, you can get the wrong answer. The best approach is to actually do a hand calculation, to do a simulation, and to actually measure it and confirm that they all three are equal to each other.
So you can actually calculate the noise. Okay,
yes,
I'm curious how you can calculate this. Is it based on some parameters from datasheet, or how do you do that?
Yes, it is.
Okay.
It's based on it's based on the spectral density. The same thing that we simulated. Well, let me just show you first for resistors.
Okay.
So here's a curve, and there's an equation as well. It's 4 times K, which is Boltzmann's constant, times T, which is the temperature in Kelvin, times the resistance, and take the square root of that entire quantity, and that'll give you the noise density. And so you can see for a 100 ohm resistor, the noise density is about 1 nanovolt per root hertz. And this shows it for 3 different temperatures. So temperature isn't really that critical. You can see all the way from minus 55 to 125. It doesn't have nearly as much impact as just changing the resistance. So that's one way you could know how much noise you'll get from the resistors.
I have a question. What kind of resistor
Sure.
is this? Is it like general for any resistor, or?
It's in general for every resistor, you're going to get this noise.
Okay, so if you are using some resistors for very sensitive circuits, you would like to go to datasheet and find this kind of graph for your specific resistor, what you are using.
No, this is generic for all resistors.
Okay, for all resistors.
Right, but this is the kind of the minimum. Some resistors will have additional noise, which is called excess noise, or it's really 1 over F noise, and that would be beyond this. So this is kind of the minimum. But if you use a good thin film resistor, this is going to be the vast majority of your noise. And when I build my designs, I'm usually using thin film resistors, and we never worry about the excess noise. And I would say in general, unless you're dealing with very low frequency design, just using this estimate for resistance noise is sufficient. So you don't need to look at the data sheet, just look at this graph.
Why there is this noise? What is it like?
It's the random motion of electrons and the resistance. And so that's why when you increase temperature, the noise goes up, because the motion increases, or if you cool it down, the motion will decrease. And then the larger the resistance, of course, the more collisions you're going to have. So that's the main reason.
Okay.
Now, if I look at a spectral density, so this curve right here is a spectral density curve that you would get for an op amp specification, or for other types of devices as well.
So this is for the amplifier?
Yes, and if you look at any amplifier, you'd see this kind of curve, where you have frequency on this axis and nanovolts per root hertz on this axis, and sometimes you'll see a little 1 over F region. And the point of this slide is that if you think of white light is all colors put together. And so all the colors in the rainbow, when you put them into a prism, you're going to get white out, or if you put white light into a prism, it'll spread into all colors. So all frequencies put together from 0 to infinite frequency, or in this case 0.1 to 100 kilohertz. If you take a sine wave at all these different frequencies and equal amplitude, you add them together, you're going to get a random signal. And so that's why we have this spectral density that's flat and basically represents the noise. And the more of this that you can filter out, the lower your overall noise will be. And I would say that actually calculating using this curve is a little complicated, and we could go through the details of that on a separate session, I guess. But if you just kind of break it down to its nutshell, if you have a bandwidth for your circuit, which is right here, the bandwidth, you take the square root of that bandwidth and you multiply it by the spectral density magnitude, which is in nanovolts per root hertz, then the square root hertz will cancel out, and we're going to get the RMS noise in nanovolts. It's very much an oversimplification, and depending on the type of noise and type of circuit, we'd have to add some factors, modify the equation, but that's it in a nutshell. You take the spectral density and you multiply it by the square root of the bandwidth, and you get the RMS noise.
Okay.
And sometimes you may have multiple noise sources that you need to add together. And since they're random and uncorrelated, generally they're random and uncorrelated in 90% of the cases, you just add them the way that you would add vectors or the sides of a triangle as a square root the sum of the squares. So for example, if we have 3 millivolts RMS from one circuit and 5 millivolts RMS from another circuit, and those two noises are adding together or combining, they don't just add algebraically, they add as a square root sum of the squares, and we get about 5.8 millivolts RMS. And when I say RMS, this would be how you would kind of calculate RMS. That's the traditional formula for RMS. But what we really care about with noise is a lot of times people will say, including myself, RMS, but actually what we're looking for is the standard deviation, which is really a very similar equation to the RMS equation, with the slight difference that the mean value is being subtracted out. So for example, if you have a noise signal and you get rid of the DC component, then basically the two equations are equal, because the average is really the DC shift on that noise signal. And so if you collect noise through whatever means, probably the easiest way to find out what the RMS value of it is to just use Excel and just find the standard deviation using Excel.
So you would collect some measurement data in time, and you would put these voltages into the Excel table, use this equation, and you would get how much noise you have, RMS.
Yes, yes. STDEV, standard deviation. And that's what I was mentioning about this. So this measurement here, it's not exact. And if you watch this, it'll move up and down. And the reason is that it's actually a Gaussian distribution, and the peak to peak is just an estimate of what you can just use the peak to peak as an estimate for finding the RMS. And if you collect more data, the peak to peak is always going to be a little bit wider. And so it's really better to take this data and pull it into a standard deviation function. In fact, let me show what the noise looks like. So we just saw a noise function on an oscilloscope that looks like this. That's what thermal noise or broadband noise looks like. And if you take all these points and you collect them together, you're going to get a Gaussian distribution. And if you look at one standard deviation on a Gaussian distribution,
so I'm sorry for interrupting. So this is basically the same graph what we saw in the measurement. Okay.
Yes,
but it was rotated by 90 degrees. Yeah.
Right.
Okay.
Yes. Yeah. So we saw this graph exactly. We saw this graph on the A to D converter, and we saw it live. And of course, it was a histogram. So if we do statistics and we look at a Gaussian distribution, if you take plus or minus one standard deviation, that's going to be 68% of the population. If we take 6 standard deviations, that's 99.7% of the population. So if I look back at my curve here, if I go from 0.4 to minus 0.4, that's about 6 standard deviations. It's covering the vast majority of this Gaussian curve. And so that's why when we estimate peak to peak, we take the RMS and we multiply it by 6, where we take the standard deviation and we multiply it by 6. And it gives us kind of an estimate of the peak to peak value. But the tail of this distribution, it goes on for infinity. So if I collect 100 points, probably the peak to peak is going to be a lot smaller, because by the probability function, we're going to end up more in the center of this. There's always a chance we'll end up on one of these tails. But if I collect thousands or hundreds of thousands or millions of points, then just by the laws of probability, we're going to fill up the center section. But some of those points are going to be on the tails. So the more data you collect, the larger your peak to peak value is going to be. So if you want to know what your peak to peak is, which normally people care about because that's kind of the error range that you're going to see. 6 is commonly used as an estimate, but it's only an estimate because it's a Gaussian distribution, and the more data you collect, the more likely it is going to be that you are outside of that range. Sometimes people use 6.6 as well because that gives you 99.9% of the population, but there's no number of standard deviations that you could choose that would give you 100% of your population. So, it wouldn't make sense to go to 7 or 8 or 10 or 100 standard deviations because it would be just unrealistic.
Mm-hmm. I have another question. Can we go back to the previous slide?
Sure.
So how did you come up with this number 6 from this graph? 0.02 is, yeah, okay.
Yeah, I didn't mark off exactly where the one standard deviation is, but just visually you could kind of do an estimate. It's about here and about here.
How do you know?
And that would be because it's just, I wonder if I have a picture somewhere.
Oh yeah, it's the position on the curve somewhere. That's
yeah.
Okay.
It's basically one standard deviation is 62%.
Okay, okay, I understand now. Oh, okay, I understand.
68%.
Okay, I understand now.
Of the population. So each, if you go to 3 standard deviations, it's a little further out. If you go to 6 standard deviations, that's the vast majority of the population. And so that's what we're looking at here. This is about 6. If I were to draw a line here to this point and to this point, 66% of the samples would be inside that range.
Yeah, okay, I understand. Okay.
And if I were to draw a line here and here, the probability is that 97% of the samples would be in that range. And it looks like 100% of them are in that range here. So, but collecting some further points, you're going to get a few that go outside of that range. The more points you collect, the more likely it is you're going to be in this region. But if you just collect a few, by the laws of probability, you're going to be in this region.
Okay.
Another kind of similar form of noise is shown here. This is called flicker noise, or sometimes it's called 1/f noise. And this is low frequency. If we look at the previous curve, we're talking about a 1 millisecond time frame. And then for this curve, very often this is in the seconds. So if you're measuring a low frequency sensor, like a pressure sensor or a temperature sensor, this form of noise might be important. And it's called flicker noise because if you look at the flicker of a candle, it has this kind of behavior. And so it's sort of a rolling with time noise. And in order to measure this, you have to reduce your bandwidth significantly. So this is really only important for very low frequency systems, which, there are many of those. So it is an important form of noise. But if you're measuring signals in the 10 kilohertz, 100 kilohertz, megahertz and beyond, you probably don't care as much about 1/f noise as you do unless you're reading something like a temperature sensor down in single hertz type bandwidth.
And why it is important to know about this? It's just an example of different kind of noise, correct?
It is. If you look at, here's a good example. If you look at a typical simulation result or a datasheet curve, usually you will have a 1/f region, and that's got this shape right here. And the reason why it's called 1/f, or you could also call it flicker, but the reason for the 1/f name is that the slope of the power curve is 1/f. Actually, what we were looking at here is the voltage curve. So the slope of this curve would be 1/√f. The broadband region is going to be flat, and this is going to have that slope. And then when you apply the filter, that's going to take the 1/f and the broadband and roll it off to the point where the actual noise will converge to a final value.
Okay, so, I'm lost. So
Okay.
this 1/f, that's the region where will be the noise what we were just talking about?
Yes.
Oh, okay, then I'm not lost.
Yeah, you can see it goes up to 10 hertz in this case.
Mm-hmm.
Different amplifiers and different circuits will be different, of course. And so it might go out to 100 kilohertz or even 1 kilohertz, or maybe it starts at very low frequencies like 100 millihertz. So it depends on the circuit, but you'll get that form of noise. And it's difficult to filter this 1/f out. So people who are doing very low frequency measurements want to make sure that they don't have this 1/f.
Mm-hmm.
And some amplifier types actually have no 1/f noise, called chopper amplifiers or zero drift amplifiers. And they flatten out this region by doing an internal calibration. And they also have good properties in terms of temperature drift. So the temperature drift is very, very low. And so
basically, because the noise is changing in 1 second or 2 seconds or 3 seconds, they kind of shift the zero and move with this noise. Oh, okay.
Yeah. So
wow.
If you think about what is let's see, the noise of an amplifier is really the offset shifting with time. So it's the input signal here shifting with time. And and if you calibrate that offset continuously, you do some kind of switching circuit on the input of the amplifier, and you essentially measure and cancel that offset change over time. It eliminates the drift, temperature drift of the offset, but it also it gets rid of this 1/f region. It flattens it out. So yeah.
I had no idea.
One other thing I could
and then
mention,
broadband noise. Let's go back. Broadband noise, that's the standard noise, correct?
Yes, that's the noise that a resistor would have. This broadband region is what a resistor would have. There's resistances internal to the amplifier and other semiconductor type noises, and then there's other noise sources that generate this 1/f.
Okay, and then the filter noise. Can you go back to the other picture with all the kind of noises? The result from the simulation.
Yeah. There we go.
This, yeah.
Yes.
And the filter noise?
Well, the filter is eliminating the broadband.
The broadband noise. Okay, I understand.
So this broadband would go out forever until there's some kind of bandwidth limit. In fact, the noise would be infinite if you didn't have a filter. But all amplifiers, all devices really will have some kind of internal natural limit to its bandwidth. And so if you don't use an actual external filter like we showed with the jumper, the amplifier itself will have a natural bandwidth limit that's going to cause this noise to roll off. And when you see this roll off like this, that's what's causing this other curve here to, I can't show it too well. Oh, wait, there we go. To flatten out. The reason this converges to a constant value is because of this bandwidth limit. If this bandwidth limit went out, to a higher frequency, then you would not see this flatten out. So it's in order to get this constant value that you would see on an oscilloscope like this, it doesn't just grow to infinity. That's because of the bandwidth limit of the amplifier or even possibly the oscilloscope. So if the oscilloscope doesn't have a wide enough bandwidth, then that will impact this. And in fact, most people have seen on their oscilloscope there's a bandwidth limit button, and the bandwidth limit button basically eliminates the noise. And it's doing it by filtering it.
Let's go. Okay, I would like to talk about this a little bit more. So what I don't understand now is why on the left picture the bigger noise is for the lower frequencies, and on the right picture the bigger noise is on the right side of the frequencies?
Oh, so the this is the
I
noise
know
per
we were
unit
talking
hertz.
about this, but I still don't understand.
But
From these graphs, it looks like...
This is the integration. So we're integrating up this area, and then we're integrating up this area. So at 10 kilohertz, we've integrated this curve.
You don't
over
need to keep
here.
moving it. Do you have there my window or something? Because I see it. I see the picture correctly.
Okay, you see it?
Yeah.
So when we're up to 1 kilohertz, this is what the integration result is going to be. If we're up to 10 kilohertz, then this is what the
I understand the integration, but what I don't understand, this is output noise, this is total noise, and they are completely different.
So
total noise looks like biggest total noise problem is in high frequencies, and in output noise it looks like biggest problem is in low frequencies.
And I think I can clarify that. You understand your problem. So if I take this axis right here, oh no, wait, let's go to the spectral density curve. And if I click on this curve and I change the axis to a linear axis, before I press the button, it looks like we've got a lot of noise here at low frequencies, and maybe that's the problem. But the thing you have to remember is that this axis is in a logarithmic scale, and so things that are quite large over here are not that important.
Now.
So that is what happens when you put it to a linear axis. Maybe this should go on a logarithmic here. Yeah. So all that noise at lower frequencies, it just shows up as a little tiny little spike, and we're integrating all of this at higher frequencies.
Mm-hmm.
So anything that happens at a higher frequency is really problematic.
So let's go back to the previous graph. So I understand now what do you mean, because when we have a look on the left graph, basically from 100 millihertz up to 1 hertz, it looks like there is a lot of noise, but it's only 1 hertz. So it's not really a lot of noise. Everything is caused by this logarithmic scale. That's what the problem. And on and that's why the graph on the right is more important.
Right. To your point, like here the noise is from 1,000 to 10,000, and so it's 9,000 wide, and we're integrating that segment that's 9,000 wide, but here we're only integrating a little bit less than 1 hertz.
So the higher frequency noise contributes much more to the noise than one big peak at 1 hertz.
Right.
Okay, I understand now.
And truthfully, this is definitely the most important curve. We care about this final value that we're pointing to here, but this curve is informative in the sense that you can see what's happening over frequency. You can see how your filter is acting. If there were some kind of instability, you might see a peaking here. You might, if you have a low frequency system, you might realize that there's a 1/f problem. And then you can compare this broadband noise to amplifier data sheets or data converter data sheets, and see, is it the right value? Because you really want to make sure that your circuit's performing to specification.
So basically this would be the same characteristic as you showed a couple of slides ago.
This one?
No. When I see the number, I will tell you the number. Go up. Number 10.
Okay.
So this is the graph?
Yeah, this is the spectral density graph. This one's pretty flat, so it's mainly broadband noise.
So this would be what we would expect from the simulation result to see in the broadband? Okay.
Yes. Yes. And I kind of mentioned that you would, if you wanted to hand calculate it, you would take this curve's magnitude and multiply it by the square root of the bandwidth of the circuit. The bandwidth of the circuit is what's limiting this.
Okay, let's go back. We can continue.
So I guess I could say that you can simulate more complex systems. So here's a A to D converter simulation, similar to what we did earlier with the hardware. And so, you know, this is in a gain of 10 or 11 really, RF over R1. And so we put 0.1 in, we get 1.1 out. There's a filter here at the output that's going to limit the noise, and you could also put a filter on the feedback capacitor. The A to D converter itself has resistors and capacitors within it that are going to limit the noise and increase the noise. The resistor voltage reference, that will also impact the noise. So noise from this will feed into the A to D converter. And all those combined is going to give us our total noise. So here we're showing kind of how you would calculate the noise for an A to D converter, or one approach at least. And so you would calculate, you would get the A to D converter noise from the data sheet of the converter, and you'd get the amplifier noise from the data sheet of the amplifier or from simulation, and then the reference noise from reference data sheet. Combine them all as the square root sum of the squares, and that'll give us our total noise. Now, sometimes amplifier noise is specified as a signal to noise ratio, and that's what's being shown here. And if you can't, a signal to noise ratio would be in decibels, and you really, for the amplifier and the voltage reference, it's going to be in volts. So you have to translate that into volts. And so this is just the math of translating this equation right here for signal to noise ratio to convert it to a voltage. And so you could use that math, and then you could add all the three components together, and you get the total noise.
Go back. I have a couple of questions.
Sure.
So what is FSR? In the first equation, there is voltage FSR.
Oh, it's a good important question. So, so the equation is signal to noise ratio, which would be spec'd in the data sheet. Let's say 90 decibels is a very typical value. 20 times the log of FSR in RMS, which is the full scale range of the A to D converter. Generally, although not always, the full scale range will be equal to the voltage reference. But in this case, it's a 5-volt reference, but we want the full scale range in terms of an RMS signal, as if it were a sine wave. And so you would basically assume that the maximum peak-to-peak input signal would be 5 volts. And so you need to convert that 5-volt peak-to-peak signal to an RMS. So you divide it by 2 to convert it to peak, and then multiply it by 0.707 to convert it to an RMS. So that's what that is. It's the full scale range of the converter. It has to be an RMS because the noise is in RMS. And that's how signal to noise is defined. And so then you just rearrange this equation algebraically to solve for this noise, because that may not be spec'd in the data sheet of the A to D converter. Frequently they'll spec signal to noise ratio. And so when you rearrange it, you then just take the full scale range in RMS, which is the RMS value of this 5-volt reference, and you divide by 10 to the signal of noise ratio divided by 20.
Yeah, okay, I understand. And
actually,
and in this picture, I have another question about.
Oh, sure. Sorry.
So in this picture, you use different kind of filter. Is there difference between using filter on the output directly or across the 10K resistor?
Yeah. So the gain of this circuit is 11 really. It's RF over R1 plus 1. And so if you were to put a capacitor across this resistor, what will happen is at some frequency, the capacitive reactance or the impedance of that capacitor is going to be close to zero. So essentially, you would short out this feedback element. But the gain of this is RF over R1 plus 1. So RF would be 0. And so that would mean that you'd have 0 over R1 plus 1, or you'd have 1. So what really happens is the gain of this amplifier
would
goes
be changing
from
with frequency.
11, right. It would change with frequency. At high frequency, at low frequency, it'd be 11. At high frequency, it would go eventually to 1 because you'd short out this component. Now, this filter on the output, it will basically short the input of the A to D converter at some frequency, and so it'll completely short out noise. So placing a filter capacitor on the feedback element, it will reduce the gain and will reduce the noise, but it's more effective generally to put a filter on the output of an amplifier. A small caveat there is that this filter cutoff frequency is quite high, and so it's not going to work well at low frequencies. And so it depends on the purpose of the filter. There's a lot of different ways of doing it, but ultimately, that idea of putting a filter on the feedback capacitor is very effective if the gain of the amplifier is high. If the gain's low, it doesn't help much. Putting an output filter is a more effective approach.
Okay, we can move to the next slide now.
Okay, so the slides here are just showing that we've simulated the noise, and here's our total noise. And then we do a similar simulation for the voltage reference. And then finally, we do the final calculation. So the data converter, this particular data converter has a signal to noise ratio of 93 decibels. And so here we convert the 93 decibels to an RMS noise value. Notice that the full scale range is 1.7, and that was calculated by taking the 5 volts and multiplying it by 0.707 and multiplying it by 0.5. So the 5 volts represents the full scale range of this, and by multiplying it by 0.5, we convert that peak to peak value to peak, and then we just multiply by 0.707. So this is the full scale range for the device in RMS, and we divide that by the signal to noise ratio. That gives us our noise, which is 39 microvolts. And then we have the 39 microvolts, and then this is the result of the simulation for the amplifier, and this is the result of the simulation for the voltage reference. All three of them are combined, and we end up here with 134. Now, notice that really the amplifier is the dominant source of noise here. And I could make these two other noise sources 0, and it wouldn't really do much to the noise. So when you're trying to make a low noise system, you really have to identify what's the problem, because of the way noise adds as the square root sum of the squares, the dominant source really will take over. And oftentimes when you add numbers together in engineering, there's kind of a rule of 10. So if something's 10 times greater than something else, you ignore the smaller element. But because we're squaring things with noise addition, there's kind of a rule of 3. If one noise source is 3 times greater than the other noise source, the larger noise source is going to dominate. So in this case, it's substantially more than 3, or at least more than 3.
And so what can you do with this? You would like to use different AD converter?
No. Because the A to D converter is 39.
Sorry, yeah, it's the amplifier. Oh, okay.
It's the amplifier.
So use filter or something.
Well, you could do a couple things. One would be you would use a different resistor network because that's generating noise. You could also use a different amplifier. There's lower noise amplifiers. And then you could add additional filtering. And yes. Those are the main points. that you could use to reduce total noise.
Mm-hmm.
And then, it's in some cases, it might be the data converter or the voltage reference that's dominating the noise problem. And so you just have to attack the component that's the worst in the system. That's
This is very
giving you
interesting because I would never say you can calculate it far before you actually design this circuit, and you can calculate it quite like correctly and realistically.
Yeah, that's the difference, I would say, between extrinsic noise and intrinsic noise. With extrinsic noise, it depends on the coupling mechanism, the shielding, the intensity of the source, the distance between them. There's a lot of variables that, impact that. And it is possible in some cases to simulate it, but it's pretty difficult. With intrinsic noise, the simulations are actually really accurate as long as the model is accurate. And maybe that's another important point that I didn't mention. So if you have a SPICE model, you can open up the model and look at it. Usually in the top header part of the model, it's going to tell you what's simulated. And in this case, the current noise and voltage noise are simulated. So you want to make sure that the model is accurate and it simulates things correctly. And once you know that it's correct, you
So
can
how do you
then,
know it's correct? There needs to be these two lines.
well, you want to see these two lines.
Okay.
And another approach to knowing it's correct, and probably a better approach, I could illustrate. So let's simplify this circuit a little bit and get rid of this output filter. I'm just going to measure the output of the amplifier directly. And the noise spec in the data sheet is going to not include the resistor noise. So we want to get rid of all that. And I'm going to go ahead and wire this circuit real quick. And I'm going to do a simulation.
So if the model is correct, you still should see some noise?
Oh, yeah. The amplifier itself has noise to it. So if the amplifier model is correct, you're going to definitely see that noise. But I'm going to go ahead and run this simulation, and we will see the noise of just the amplifier, not the resistors. And so usually you want to change this to a logarithmic axis to match the normal way these are displayed. And now I'm going to very quickly get the data sheet for this device. So in the data sheet, you can see the noise curve. And you can see, let's change the axis here to make this match a little
similar.
bit. Okay. So now you can see 100, 100, 10, 10.
Nice.
So you can see it's very, very accurate. And so that's one way to actually be very thorough and really make sure that your model is accurate. You have to get the data sheet and look at the noise density curve. And then you would simulate your model with no resistors, and you could find out the total noise. Incidentally, the curve next to this is the 1/f noise, and they call it the 0.1 to 10 hertz noise curve because it's very low frequency. And so you could kind of see that rolling motion, and what we're looking at is this low frequency kind of noise.
Okay, we can go back to our presentation.
Well, we've kind of covered a lot of what I've done, what I plan on doing today. I do have this measurement example here that relates to the EVM, the evaluation module, And I could do a simulation here and show that the measured result, for example, would be something on the order of 166 or 85. I've got two different amplifiers with two different filters. So these are the two possible outputs for these two different amplifiers. And this is the measured noise. And the simulated noise is right here. So the simulated noise would be 175, and this is 166 measured, 88.4, 88.5. That one's almost perfect. So this demonstrates really how accurate noise simulation can be. And it should be exact, but there's some tolerance in the devices, and there's tolerance in the resistors. The actual bandwidth limits will be slightly different because of parasitic capacitances, and the models aren't always perfect. So it's generally going to be pretty close, within 20% or perhaps better. And of course, even all the assumptions is that these measurements are made at room temperature. The temperature even affects the results somewhat. Should I go through simulation and then show that the measured results match that?
So first, I would like to clarify this table. So these noise 1, noise 2, these are the amplifiers which are on your board, correct? One is the yellow one, the other one is the red one.
No, this is the this board right here. And here's the two circuits that we're going to look at.
Okay.
Notice that they both have the same amplifier, same input signal, the same gain. If you take 100 divided by 10 and add 1 to it, it's the same as this. The resistor values are different. So this one over here, noise 2, is going to have less noise than noise 1 because larger resistors generate more noise. The bandwidth limit is actually the same for both. Notice the capacitor is smaller here than here. And the idea is that you can calculate the cutoff frequency by taking 1 over 2 pi times the R and C. So because the resistor is larger here, we compensated for that by making the capacitor larger over here to keep the bandwidth the same. So the only variable in these two circuits is the magnitude of the resistors. Everything else is the same.
And you have this circuit on your development board, and you just switch between them by jumper or something.
No, I actually I have these little coupon cards, and so you can remove them and install them. And all these coupon cards illustrate different things, such as distortion and so forth. These two are the coupon cards for noise.
Okay.
So right now we have one amplifier installed, and if I pull up the software right here and hit capture, let me disconnect my external signal, and I'm going to change the jumper so that I use an internal low noise precision reference as the input with 0.1 volts. So now we're applying 0.1 volts to the input. You can see the picture right now is the last one we took with the 60 hertz noise. And then if I capture it, we now get rid of the 60 hertz noise. And so
I look this is very low noise. It's like, what, less than 1 millivolt.
So yeah, it is. And actually, it could be lower. The part itself is going to be much lower noise. So the histogram gives you a lot of information about the noise. So the code spread is 21 codes. That means that's how far we're spreading across in this region. The standard deviation is 2.22, or sigma is 2.22. That's the RMS noise, but it's the RMS noise in codes, not in volts. So whenever you're dealing with the A to D converter, you can convert the codes to volts by multiplying by a factor. And so this table here shows that factor. So the least significant bit is the factor that you use to convert codes to volts. And so the full scale range is 5 volts, and this is a 16-bit converter. So we take the 5 and we break it into 2 to the 16th pieces, and it's 76 microvolts per bit. And so if we take that standard deviation that we measured,
2.2.
2.2,
I think,
and we multiply it
Yeah.
by 76, then the peak-to-peak noise we're getting is 100 and, or no, the RMS noise we're getting is 166. And then if we took the 166 and multiplied it by 6, that would give us the peak-to-peak, or kind of the code spread that we would expect.
So basically, this number 166 is the number which you have in the table, correct?
Yes.
So, okay, and in this table, we will see all the results between different ways of getting the noise.
Well, yes, all the different components. So the amplifier noise is shown here. That's 170 microvolts. The A to D converter noise is shown here. We talked about how you would calculate that earlier. And then the reference noise is from the data sheet or from a simulation of the reference. So these 3 noise sources add together as the square root sum of the squares. And I came up with 175.
Wow.
Yeah, and so in this case, it was 2.18, so it's a little bit different than mine, but not much from what we're measuring now. And if we look at the calculated result, 166 microvolts, that compares very well to the actually predicted, or I should say, the measured result of 166 compares very well to the calculated value. Now, if I take this amplifier and pull it out, and then I install carefully so I don't short it out, install the different amplifier.
That's the noise 2?
Yes, that's the noise 2. And so noise 1 was a little bit higher than what noise 2 should be, because noise 2 is smaller resistors. So if I collect the data, I get 1.2. And you know, in previous measurements that I made, I got 1.6. I got about 88.5, and the calculated value is 88.4. So you really can see that you might get a little bit of error, you know, 175 versus 166. But if you're really modeling everything correctly, they should be essentially equal. Of course, all components have tolerance to them. So, you know, the amplifier, the resistors, and so forth. There's going to be all sorts of tolerances. The capacitors used in the filter are going to have tolerance. It's going to change the filter cutoff, and so that's why you'll see some variation. But it's pretty close. So the one thing I did not talk about is EMIRR, and you know, I mentioned it, but I didn't show the slides for it. So I could go through this now. And
because this is the better amplifier, correct?
Yes.
Okay.
Yeah, the yellow versus the red amplifier. So here is here's an overview of what EMIRR is. And so this is the internal workings of an amplifier. And it's not really super important to understand exactly what's going on here, but most op amps are going to have a differential input stage, and they're going to have some ESD, or electrostatic discharge protection diodes, and then even subsequent stages and elements that are kind of simplified are going to have more transistor junctions. So the main point here is that we have some high frequency signal, hundreds of megahertz or gigahertz. It's being applied to an amplifier that has a bandwidth of, you know, maybe a megahertz or 10 megahertz. Some of them even have, you know, hundreds of megahertz of bandwidth, and some even have very low bandwidths, like tens of kilohertz or hundreds of kilohertz. The point is, this RF signal is way, way, way higher than the bandwidth of the amplifier. And if you think about it from a theoretical perspective, you'd think that that RF signal should just be attenuated by the amplifier because it's outside the bandwidth of the amplifier. But in fact, what really happens is this RF signal gets into the amplifier and it's rectified by the diodes and internal junctions of the input transistors. And it's converted from an RF signal to a DC signal. It causes the input offset voltage of the amplifier to shift, which basically will cause the output signal to shift by a small amount, which could introduce a DC error or distortion. But the nice thing is that many of the newer amplifiers will have a built-in filter before we get to the various transistor junctions. And this filter, yeah.
So basically,
Yes.
this is the filter, this is what we are going to explain. This is the filter which eliminated, for example, the walkie-talkie noise.
Yes, exactly.
Okay, so let's have a look how it works.
Right. So it's just a simple RC filter. There's a differential filter right here and some common mode filters. And you can see it has a fairly high bandwidth to that filter, much higher than the bandwidth of the op amp. And of course, it has to be higher than the bandwidth of the op amp. You don't want to limit that. And so the RF signal will be attenuated before it gets to the junctions. And what we do with our modern amplifiers is we test them. First of all, we design them to include that filter, but we test them to make sure that we can give you a spec that you can look at to see what the electromagnetic rejection ratio is. So the way we test them, it's pretty simple. We just apply an RF signal to the amplifier. And of course, being that it's RF, you have to make sure that you don't have reflections. So we connect that signal source to the input using impedance matched type situation. We put the amplifier in a simple buffer configuration. Ideally, you would expect this high frequency signal to just completely disappear because it's way higher than the bandwidth of the amplifier. But in fact, it causes the offset of the device to shift, and even some RF will leak through the device. And so to eliminate the RF that leaks through the device and just look at the offset, we have a low pass filter, and then we measure the offset shift with the digital multimeter. And here is the final result. So these are 4 different amplifiers, 1, 2, 3, 4, shown here, and they have different bandwidths. This is the inherent bandwidth of the device. And so this one's 350 kilohertz all the way up to 5.5 megahertz. And so some of these have built-in filters, but this one down here does not. And you can see that the one that does not has very poor EMI rejection. But the ones that do have those filters have much better EMI rejection.
So
and of
higher
course,
is
the lowest
better,
bandwidth
yeah?
of them all. Yeah, higher is better. So yeah, so this is very much like the SNR. It's 20 times the log of the output signal divided by the input, and so this is a very high rejection ratio, and then this is not so good. So so this device that has lower bandwidth has the best rejection. It's harder to get good EMI rejection for wider bandwidth amplifiers because that filter needs to be pushed out to higher frequencies. But all 3 of these are fairly effective, better than the device that, it's a little bit older generation that doesn't have that filter. And the 2 that we were comparing aren't shown here on this page, but one of them, of course, had really good EMI rejection, and the other one didn't have quite as good EMI rejection. And so when I keyed the walkie-talkie, the EMI rejection basically stopped that signal from really perturbing the devices. And the other one kind of allowed that signal to shift the offset.
Nice. That's good to know how it works. I forgot, we should mention your book.
Oh, okay.
So I know you have this book which you published, correct?
Yes, and it's on the topic that we did today. although I don't have any data converter, information in it. And then I also have this little, it's a PDF version of a pocket reference, it's called, but basically a lot of engineering graphs and tables and relationships are summarized in this.
Thank you so much, Arthur.
Sure.
This was like super cool because I have never covered this topic. So I really hope everyone who likes analog and sensitive circuits, low noise, I really hope they will find it useful. Thank you.
I hope so too.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.